Hello everyone. So we are now discussing different physics associated with sensors. So in the last lecture we have discussed physics associated with magnetic sensing, and we have seen how magnetism can help, or different phenomena associated with magnetism can help in developing different sensors. One of the most important magnetic phenomena that is related to sensing applications is Hall effect, and we have already discussed what is Hall effect, and we have seen how Hall effect can be used as a sensor, as in if you take a semiconductor block and if there is any magnetic field around that, and then how to engineer that semiconductor block or say a semiconductor chip so that it can detect the change in the magnetic field around it. And today we will move to a different type of sensing, which is known as acoustic sensing. You have seen lot of acoustic sources in the environment, and there are a lot of detectors as well. So if I give you an example of an acoustic sensor which is created by nature, for example the ear that we have, or the ear of any creatures is capable of detecting sound, and then the same sound goes to your brain to comprehend what that sound means if somebody is speaking. If there is any other sound which doesn't have any significance, then also it is capable of detecting that particular sound. Now the idea is, if you have an acoustic source, then it will emit sound energy. It will emit sound, and then if that sound hits a detector, that detector will receive that energy and then will convert it to a certain form of other energy. So there is a transducer effect again associated with the same. Now if you have a acoustic transmitter and receiver, that is transceiver, then what you can do is you can use that transceiver, or for example say this is an acoustic transceiver, you can use that transceiver and you can generate sound. That sound may get reflected from an object kept at a particular distance d, and then you can detect the reflected sound. Now if you can calculate the time it takes, or the time this sound energy takes to go and hit this object and come back to the receiver section, you can actually measure the distance, because the sound energy or the sound has a specific velocity in a certain medium. So currently in air you have a specific velocity of sound. So if you consider that, you'll be able to understand that it's not actually very difficult. You have velocity v, and you know the time this sound takes from the source to the object and then again to the source, which probably can be given as t total. Then your distance from the source to object for this sound will be 2d. If it is d, for example the distance between source and object is d, then the sound will travel 2d distance, because it will go from source to the object, that is d distance, and then again it will go back from object to source, so another d distance. So if you add them up, it is 2d distance. So you also know the total distance as 2d. So your total distance 2d is equal to velocity of sound in this medium into the total time it took. So from here the value of d is Vs into T total by 2. So this particular transceiver can act as a can be used for distance measurement. So in this case, you have a transceiver which acts as a instrument that can measure distance. So acoustic sensor can be used for measuring distances of several objects or different objects. Okay. Now this is one of the applications, and you'll find that most of the or many of the acoustic sensors are used for this purpose. Okay. So one of similar principle you may find in bats. They also emit a certain sort of sound, and then from the reflected sound they get to know if there is an obstacle in front or obstacle ahead or not. That is how they decide. So it's already there in the nature. The sound that they emit is in the range of ultrasonic sound. So if you categorize the sound sources in terms of frequency, you'll find anything less than 20 Hz is actually infra sound or infrasonic sound. Then 20 Hz to 20 kilohertz is the sound which is audible sound. You may write it audible sound. And then anything beyond 20 kilohertz is actually ultrasound or ultrasonic sound. So in this case, this range is something where we can listen to a particular sound. So it ranges from 20 Hz to 20 kilohertz. That is the range of human ear, the frequency range of sound that human ear can kind of comprehend. So a lot of application you will find where ultrasounds are used. So one of the major reason of using ultrasound is, first, it's beyond our audible range. So even if you use this sensor, it will not create any disturbance. Number two is because the sound frequency is quite high, so it can detect even smaller objects. So one of the basic thing related to wave is, if the object size is less than your or less than the wavelength of the energy, then it will not be able to detect it. What I mean by that is, for example, if your wavelength is 10 millimeter, the wavelength of the energy is 10 millimeter, then this particular wave will reflect back from an object having dimension more than 10 millimeter. It can't reflect back from an object which is less than 10 millimeter. So that is why if you increase the frequency, the wavelength will get reduced and you will be able to detect even smaller objects. So in that sense, ultrasound will be very much useful for various smaller object detection as well. And as far as the sound wave is concerned, you will find that sound wave actually is a longitudinal wave, and once sound wave travels through a medium, it creates rarefaction and compression. What does that mean? For example, if you take this as a medium, and in that medium there are different, say, molecules or particles present, so you'll find that when sound wave progresses through that medium, it will create a compression somewhere. That means molecules will come closer or particles will come closer and will create a high pressure zone, and then just next to it there will be a rarefaction, that is the molecules are away from each other. So that is how it progresses. So sound wave is like creating a variation of pressure in the medium. So here I have given you the equivalent description, or I would say equivalent visualization of the sound wave. But sound wave actually is not a transverse wave, it's a longitudinal wave, and it moves like this, where in the compression region or the region where it is compressed, the pressure will be bit higher. So this is how the sound travels. Now the advantage or the specification of a acoustic sensor is the detection range is usually 0.1 to 10 meter. Then the resolution that you get is in mm, although it depends on the transducer, what is the frequency of the wave that is transmitting from that transmitter. So transducer, I already have said what is a transducer. So it depends on the transducer. Then the field of view is 5 to 120 degree. What does that mean? For example, if you have a sound source, then usually you'll find that it can cover from 5 degree to 120 degree if it is a point sound source. So it can cover this range. If there is anything in that range, it will be able to get reflected from that, or it will be able to provide information from that. Then the power consumption associated with a acoustic sensor or ultrasonic sensor is usually between 72 to 336 milliwatt for active condition. For a passive condition, it may be few milliwatts, but when the sensor is active, it consumes around 72 to 336 milliwatt. The advantages that you get for a ultrasonic sensor is it can detect solid and transparent glasses. So if you have a transparent glass, many a times you may find that optical sensor is not able to detect it because it goes through it. The sensor, the light goes through it, so you don't get a reflected signal back from a transparent material if it's an optical sensor. But in case of acoustic sensor, you'll be able to very easily detect transparent glass as well, because anyways the sound signal will reflect back from that transparent glass. Then it can also detect object in smoke or gas filled environment. So if there is a situation where you find a lot of smoke around, so an optical sensor may not be suitable in those cases. So what you can do is you can use acoustic sensor, and you will be able to get reflected signals from various objects, even if it is very hazy visually. So these are the advantages that you generally get for acoustic sensors, and you will find a variety of application associated with acoustic sensor. Now let us see what are the usual geometries that we use for an acoustic sensor fabrication. So acoustic sensor can be resistive, and it also can be capacitive. So in case of resistive type, what you do is you put some conductive material, say carbon granules, in between, say a conductive back electrode and a conductive front diaphragm. So if you have a diaphragm, then you put carbon granules in between that diaphragm and a conductive back electrode, and then there are spacers in both the sides. So what you will see, if there is a sound wave that is interacting with that diaphragm, the diaphragm will anyways move back and forth, and based on that movement, you'll find that the resistance of this entire geometry will change. If you take, say, output from these two ends, so you'll find that the resistance will change based on the pressure applied. So if the sound wave is interacting with this diaphragm, it will deform, and because of that deformation, you'll find the resistance will change. So the theory that is associated with that change in resistance can be attributed to percolation theory, where if there are different granules, say for example, say there are different granules present in here, and due to deformation, these granules will arrange themselves in a way that you will get a shortest path somewhere, and the conductance of the entire geometry will depend on that shortest conductive path. So based on pressure, this conductive path or the shortest conductive path will change, and you will be able to see a variation in the electrical response. Say in this case, it's the resistance, right? So a resistive sensor can be used for detecting acoustic signal, In a similar geometry, if you replace this carbon granule with any dielectric material, and then if you start taking response, a capacitive response across that arrangement, you'll find that again, because of this interaction of sound wave, the distance between the diaphragm and the back electrode will change, and if the distance changes, definitely the capacitance associated with the system also will change. So if they come closer, the capacitance will be higher, and hence you'll be able to detect the sound signal based on the deflection of this diaphragm, right. So the geometry wise, both of the structures, resistive and capacitive, more or less are same, and you can use this for, say, a microphone. The purpose of a microphone is to take this acoustic energy and then convert it to an electrical signal. In both these cases, the acoustic energy that is interacting with the diaphragm will definitely get converted into an electrical signal in terms of resistance or capacitance, as it is shown over here. Now, one thing which is very common in most of the acoustic sensor is that diaphragm. So you need a diaphragm meaning a thin layer which will deflect or change its shape if sound interacts with that. So for example, in ear also you'll find there is a diaphragm present inside the ear. When sound comes and interact with that diaphragm, then this diaphragm also deflects. So once you have that diaphragm, you can put it in different arrangements in order to create a say acoustic sensor or acoustic detector. So in most of the cases, I would say almost in all the cases, you'll find that this diaphragm is present, because you anyways need the deflection from the sound wave. Now there are some other types of sensors as well. For example, this is an example of moving iron microphone, where the diaphragm is connected with an iron structure, and then it is placed inside a magnet the way it is shown, and then you have a coil associated with it. Now once this diaphragm deflects, this iron structure will move back and forth, and this will create a change in reluctance in the entire magnetic circuit. So reluctance is nothing but the magnetic circuit equivalent of electrical resistance, right. So electrical resistance is V equal to I into R. So if you have a voltage, and the relation between the voltage and current in a conductor is V equal to IR, where the proportionality constant is R, resistance. Now if the physical significance of R in almost all the cases, this is true for a ohmic conductor, but even for non-ohmic conductor, you'll find resistance is a property that actually restricts the electric current to flow inside a conductor. So in case of magnetic circuit, magnetic reluctance does the same thing, okay. So for magnetic energy to flow, or magnetic flux to flow, better to say. So if there is a diaphragm and if there is an iron associated with it, the way it is mentioned over here, now the deflection of that iron block will actually change the reluctance associated with the magnetic circuit. We also may call it a moving or reluctance based microphone, or reluctance changed based microphone, and it is also called a moving iron based microphone, or moving iron microphone. So in this type of structure also you will be able to detect the acoustic energy. So this also can act as a acoustic sensor. Similar to that, there is another structure which is known as moving coil microphone, wherein you attach a coil to a diaphragm, and then when this diaphragm moves, and in fact this coil is now connected to a magnet as it is shown over here. Now if this diaphragm moves back and forth, the coil will also move back and forth, and that will change the magnetic flux inside the coil. If you take two connections from the coil, you will find that because of the change in magnetic flux inside the coil, you will get certain sort of electrical output from this coil. Now, the output will depend on the deflection of this diaphragm, and the deflection of the diaphragm will depend on the sound that is interacting with this diaphragm. So, this type of arrangement is also possible, and you may find that in several microphones this moving coil arrangement is used. So, these are the techniques or geometries that one can use to calculate or to detect or measure the acoustic signal that is interacting with this particular system. So, they act as an acoustic sensor. There are many other types of sensors, for example, say ribbon based, where you can actually use a ribbon and then this will be connected to one capacitive structure. If this ribbon actually moves towards the back electrode, then the capacitance of the system will change. So, this type of arrangement is also possible. You may also make a MEM sensor, micro electromechanical sensor, where you can use a cantilever, where this cantilever frequency will depend on the sound that is interacting with this particular cantilever. Say if there is an ultrasound that creates a deflection in that cantilever, and if you have an piezo resistive material attached to this cantilever, the resistance of this, or piezoelectric material attached to this cantilever, then piezoelectric property or piezoresistive property will change based on the deflection of this cantilever, and then you can quantify that electrical output to the acoustic signal. So, these are some basic structure associated with acoustic sensor. However, if you want to calculate the response associated with that, for example, for the resistive or capacitive type, then it is basically a capacitive sensor. So, the calculation will remain same as we have discussed in case of capacitive sensor. If there is a deflection, then you can very easily calculate what is the capacitance associated with that particular deflected state, and then you can actually create or actually can figure out the mathematical equation associated with the acoustic signal detection. So, that is how one can calculate the or mathematically derive the equation associated with this particular sensing method. But in this lecture, the purpose of this particular lecture is to provide you the idea how acoustic energy also can be detected using different geometries. What are the different phenomena or physics associated with it, and how we can actually make a acoustic detector out of a particular geometry. So, we already have seen different types of acoustic sensors, and also have seen what are the various considerations associated with acoustic sensors. But even in this discussion, you probably have noticed that even we were discussing regarding this acoustic sensors, the major working principle associated with the sensor was like capacitive, and in some cases it's like resistive sensor only, because even in case of acoustic sensors, you have usually a membrane which is which deflects in one direction, and then you have an fixed kind of electrode. If it deflects in one direction, then definitely the capacitance associated with that arrangement will change. Or at the same time, if there is an active material which is a kind of resistive, and then if it deflects in one direction, then the total resistance associated with this arrangement will change. So it is either a capacitive sensor or a resistive sensor, or it can be an inductive sensor as well. We already have seen several other types of acoustic sensors in the discussion. So the calculations associated with this particular types of sensors will be similar to the one we have done in case of capacitive sensor or in case of resistive sensors. There is nothing different as such as far as the resistive arrangement and capacitive arrangement is concerned. However, if you look at the application of acoustic sensors, then you'll understand that there is a huge kind of application as far as the acoustic sensors are concerned. One major application in the field of acoustic sensing is like biomedical engineering. So, in biomedical, you'll find there are a lot of diagnostic devices that usually use acoustic sensors only. For example, say echocardiogram, then you have ultrasound imaging. So all these imaging techniques are based on acoustic response of the based on the acoustic transducers. So there is a source of sound which passes through, say, the body part, and then it gets reflected back, and then from that reflection you have a receiver present somewhere inside the transducer that receives the signal, and then it converts that into images, or it gives you different parameters associated with human health or human body. So that's why this particular type of sensor is really important. And you also will find that acoustic sensors can also be used to measure distance. uh, I think I already have discussed how it works. If you have one source and if you have one detector, then it reflects back from the source of the acoustic wave, sends a signal. It then reflects back from a kind of barrier present in front, and then comes back to the receiver. Now from here you can understand what is the distance between the object and the transceiver. So this is another application of acoustic sensor. But what you should uh, keep in your mind is what type of sensor or what kind of combination you can use. I already have given another application, which is microphone. I've given you the example of moving iron microphone, moving coil microphone. So in that case, we are basically using a capacitive sensor in order to convert the voice into an electrical signal, and then from that signal we are actually amplifying it to a larger extent. So that is again a very well known example of acoustic sensor. But in many cases, in fact in all the cases, what we use actually is an acoustic transducer. Okay, so a transmitter as well as a receiver. So you use a transmitter as well as a receiver. That is the combination that you use. But if it's only the receiver, that is the sensor, then in that case it's the microphone. So if you have a microphone, it's like the voice is interacting with the microphone sensor arrangement, and then we are converting that signal, amplifying that signal for a different usage, or to spread it across to a larger audience. So in case of microphone, it's like the sensor only, there is no transmitter, because the source of sound in that case is your voice or human voice or any kind of other sound for that matter. Okay, so this is more or less the basic details associated with an acoustic sensor that we have discussed. And I just wanted to summarize to some extent to give you an brief understanding about why acoustic sensor is important and what are the calculations. As we have said, that calculations here are more or less done beforehand, while we are discussing while we were discussing capacitive sensors and resistive sensors. Now, in the upcoming discussion, we will see another very important or widely used sensing technique, which is microfluidic sensing. You will find this type of sensors are used in biosensing applications. It is widely used nowadays, and we will see how microfluidics can also help in making different types of sensors. Till then, thank you.